Okay, in this example, I wanted to show you how to calculate moments, and the way I'm going to do this is I'm going to make a structure and I'm going to have it line up on the grid line so that you can easily measure distances without doing a lot of calculations. Okay, so I'm just making sort of a random structure here. This can be made out of steel or whatever. Alright, and I'm going to label some points on there. Let's do that dark blue. Here's point A. Let's make this point B. And over here, point C. Okay, next what I want to do is put some forces on those on this structure, and we're going to calculate the moments that are generated at various points. Okay, so let's put a force right here, and we'll call that a 100-pound force. And let's put another force right here. We'll call that 50-pound force. And a third one, let's put that here. 200-pound force. Okay, so let's assume that all the points on the grid here are 1 foot apart. Grid spacing 1 foot. Okay, so if I wanted to calculate the torque, if this is a rigid structure and I pinned this structure at point A on a pin and applied these forces, how much torque would be at point A? That's the question. All right, so you get this by calculating moments. All right, and so we talked a little bit about that before. All right, so let's look at the torque at part A. We're basically looking at the sum of moments about point A, and we're going to take counterclockwise to be positive. Okay, so we've talked about torque being in foot-pounds. All right, and so here's the idea. All right, let's take a look at the torque from the 200-pound force first. Okay, so there's when you're looking at calculating moments, you look at the line of action. Okay, so the line of action goes down this way, and you can slide the force anywhere along the line of action, and what you're looking for is the parallel distance. Okay, so perpendicular distance. So here's this line of action. The perpendicular distance in this case is right here. Okay, so I measure that according to the grid. That's 3 feet. Okay, so I'm going to put down the 3 feet, and then I'm going to multiply by the 200, and then I'm going to figure out what's the direction of rotation. So if I put this force pushing down, that would cause a rotation. Can you visualize that? It would cause a rotation to be clockwise, so this would get a minus sign on it. Okay, so that's the first one. All right, so let me undo all those extra lines. Okay, we don't need the orange line. Put that one back. Okay, and let's do this for the 50-pound force. All right, so what is the closest distance? Well, let me pick this up here and slide it. I got the wrong thing. All right, so this is the line of action. All right, it goes this way. So can you envision where the vector is perpendicular to A along this line of action? It's right here, right? So as I slide that up along the line of action, the perpendicular distance is 1, 2, 3, 4, 5, 6, 7. Okay, so that means what we have for the torque is 7 times 50, and then this is causing a counterclockwise rotation. Okay, and so I lost this minus sign. So this would be a plus sign. Okay? All right, so hopefully you're with me. Now let's go on to the 100-pound force. Again, we consider the line of action. Okay, so we pick this up, we move it along that line of action. What's the perpendicular distance to point A? It's only 1 foot, right? So you get to where you can just see it. You don't have to, really slide it over. All right, I can do that on my iPad. But you can see that. So this would be 1 foot times 100. And then which way is it causing the rotation? It's counterclockwise, right? So if I push this way, it would cause it to rotate like that, which is clockwise, okay? And so because it's clockwise, that would need a minus sign. Okay, so you add all these numbers up and you get the answer in pound or foot-pounds. All right, so that's tau A. All right, pause the video and try to do tau B. All right, hopefully you paused it and you're back. Tau B, all right. So let's consider the 200-pound force first. That one's easy. It's already lined up with the line of action, and we count the units over 1, 2, 3, 4. This rotation would be counterclockwise, so it'd be plus 4 times 200. Okay, so that's the torque or the moment due to the 200-pound force. Now notice the 50-pound force goes right through the point, right? You're not generating any torque if you just push straight onto the point. So there is no moment generated by the 50-pound force. Okay? And then finally, the 100-pound force, you slide this line of action like we've done before, slide that through. Now it's perpendicular to B. All right, and so that would be 1, 2, 3, 4. All right. 4 times 100. And which way does the rotation go? Well, it would go clockwise, so it needs a minus sign. All right, so you calculate that number. That would be the torque in foot-pounds for point B. Okay, let's do tau C. All right, for C, what do we have? All right, so just by inspection, let's take a look at the 200-pound force first. So I don't need to pick that up and move it. I get the idea now. It's just counting these grid lines. 1, 2, 3, 4, 5, 6, 7, 8 is the closest distance to the line of action for the 200-pound force. So it'd be 8 times 200. Which way is the rotation? Okay, so if that's pushing down, that would cause a counterclockwise rotation, so that would be a plus. Okay, now for the 50-pound force, I'm already got that along the line of action. I already got the line of action perpendicular to C as shown in the figure. Okay, so I count that off. 1, 2, 3, 4. That's 4 times 50. All right, and this rotation would be clockwise, so I would need a minus sign. Okay, and then finally for part C, you have the 100-pound force moving in the x direction. The perpendicular distance is 2. All right, so that'd be 2 times 100. All right, and then what kind of rotation does that cause? That causes counterclockwise, so this needs to be a plus. And this answer would also be in foot-pounds. Yeah, I don't actually calculate that, but you could add up all the numbers and get it. Okay, so if you pin this object, the only way things don't actually move is if the sum of forces or sum of moments is equal to 0. So if you pinned at point A, that's not going to be, that's not 0. Okay, and so this thing is going to rotate. All right. All right, so that's the idea. Later on when we talk about applying this idea of moments to static applications, we're going to find that the sum of moments about any point that we choose is going to be 0, and we're going to use that to help us solve problems. Okay, so I'm going to do one more example video. I'm going to pause or stop this one for now, but we'll do another example where we take forces that operate not just in the horizontal and vertical directions, but that operate at any angle theta, and we'll figure out how to calculate moments for that.